Okay, for the presentation today, I want to do some of the basic problems related to hyperbolic trig functions. Let's look at the following problem. It says, show the following identity. Show that sine hyperbolic of x plus y is equal to sine hyperbolic of x cosine hyperbolic of y plus cosine hyperbolic of x sine hyperbolic of y. Those of you remember from trigonometry, there is a very similar identity for the regular sine function. Sine of x plus y is equal to sine x cosine y plus so on. So this is a hyperbolic version of it, which looks exactly the same. Sometimes some of these identities are different from the traditional trig by having minus instead of plus or plus instead of a minus. In this case, it's exactly the same look. How do we prove these things? Well, in hyperbolic trig functions, the proof is actually a lot easier than the regular trig. How do we go about this? Let's remind ourselves of two things. One is that cosine hyperbolic of x is defined to be exponential of x plus exponential of minus x divided by 2, and sine hyperbolic of x is defined as exponential of x minus exponential of minus x divided by 2. So our approach will be to write the expression for the left hand side, also write the expression for the right hand side, simplify one of these sides until it looks like the other one. So here's the background. Remember, we had these two definitions. Now we go ahead and write left hand side of this identity. So left hand side of the identity, that is sine hyperbolic of x plus y. What is that? Well, here's a definition of sine hyperbolic. Instead of x, now I have x plus y. So I go ahead and replace x here by x plus y. It becomes exponential of x plus y minus exponential of minus. Now instead of x, I'm writing x plus y. Remember, we need that parenthesis over there. Divided by 2. Okay, there isn't much to do here, not much simplification that can be done to the left hand side. We go after writing the right hand side, see if that one can be simplified. Right hand side of the identity, I don't rewrite this thing all over again. Instead of sine hyperbolic of x, I write its equivalent expression. It's exponential of x minus exponential of minus x divided by 2. Cosine hyperbolic of y, that comes from here, except that x has been replaced by y, so I have to multiply by that one. It's exponential of y plus exponential of minus y divided by 2 plus cosine hyperbolic of x. That's just a copy of this, so I write exponential of x plus exponential of minus x divided by 2. Sine hyperbolic of y, just same as this. Instead of x, I write the y, so times exponential of y minus exponential of minus y divided by 2. So what is our job now? Our job is to actually multiply this thing out, clean it up, and show that this is the same as that. Remember, we are trying to show that this left hand side and right hand side are equal. Here's our left hand side, here's the expression for that. Here's the right hand side, that's the expression for that. Either we have to make left look like right, or we have to make right look like left, or we have to make both of them equal to something else, and then we'll be done with showing the identity. So how do we go about doing that? We just need to be patient and multiply all this thing out, see what happens. So I write right hand side, 2 times 2 is 4, this 2 times 2 is also 4, so common denominator for all of these things is a 4. I might as well just put it aside. 1/4, so this 1/4 reminds us of this 2 times 2, and another 2 times 2 is a common denominator. Now I go ahead and multiply the numerators. Exponential of x, I multiply it by that, then by this, then minus exponential of minus x, I multiply by this one and the next one, and just write them all out. Let me remind you of some basic rules of exponents. If you have exponential of a times exponential of b, what do? You add up the exponents. So basic rule of exponents, we are going to be using that a lot here. So let's go back. Exponential of x times exponential of y is exponential of x plus y. This first times the second, alright, plus exponential of, the exponent here is x, exponent here is minus y. We have to add them up. Next, I have minus times plus, so the overall sign is going to be minus. Minus exponential of, this is minus x, this one is plus y. Minus x plus y. Finally, this one and that one, sign up front minus times plus, it's a minus, and the exponents minus x and minus y. Now we have to repeat all of this again with the second term here. Let me make some space. So exponential of x times exponential of y, that's exponential of x plus y. First times second is minus exponential of x minus y. Notice what happened. This is plus, this is minus, so the overall sign became minus. The exponent x minus y, and that's the net exponent here. For the next one, I have plus times plus, so that's going to be plus exponential of minus x times plus y. This is minus x plus y. Finally, this second times the second. The signs, this plus times minus becomes minus, exponent minus x from the first, minus y from the second. Notice this and that are the same. This and that are the same. This and that are the same, except that signs are different. So this plus and minus cancel each other out. Minus and plus cancel each other out. These two double up. These two double up. So what I get is 1/4 of this and that became 2 exponential of x plus y. This term and this term, they just collapse to 0. This 2 also collapse to 0. These two double up became minus 2 exponential of minus x minus y. Well, 2, I can factor it out, simplify by 1/4. That's going to make me 1/2 exponential of x plus y, and here is minus exponential of minus x minus y. This is essentially as far as we can go. If you want to go ahead and check the proof right now, we are done. This was the left hand side. This is the right hand side that I simplified and finally arrived at here. Now compare this versus that. Do you see that they are the same thing? They are written a slightly different way, but they are the same. This factor of 2 in the denominator, same as this 1/2 here. Minus parenthesis x plus y is same as minus x minus y. So these two turn out to be the same. So we show, let's write out here is exponential of x plus y So we showed that the left hand side is equal to right hand side. Therefore the identity is proved. We are done. This is a major identity. Good to see it once and perhaps even memorize it. Now you can go ahead and prove a similar identity for cosine hyperbolic. It's a good practice. Do the following. Show. So we are done with this. Show that exact same thing happens with cosine hyperbolic of x plus y. That is cosine hyperbolic of x times cosine hyperbolic of y plus sine hyperbolic of x sine hyperbolic of y. Notice some differences here. Cosine, cosine, sine, sine. It's the same function appears. For the sine, it's mixed, sine and cosine, and again another cosine sine. So it's one difference. One difference between this and the traditional trig identity of same beginning is that over there, when you're using the plane sine and cosine, this is supposed to be negative instead of positive. So you go ahead and prove this problem on your own. Let's go ahead and do some differentiation problems. Here is a problem I choose from this list. Let's say problem 32. So this is problem 32. This in your text right now, this appears as problem 12. Problem 32 says take g of x is equal to sine hyperbolic square of x. Find out g prime. So we have to remember certain basic formulas. One of these is the following. If you have some function raised to some exponent, you want to differentiate the whole thing, the rule is the exponent comes in front, the exponent is lowered one notch, so n becomes n minus 1, and one thing not to forget is the derivative of the base itself, f prime of x. So that's our generalized power formula. What happens here? This exponent comes in front, the function is going to be written to 1 less than the old exponent, so that was 2, we have to lower it one notch, it becomes 2 minus 1, which is just 1, and then derivative of the base sine hyperbolic of x has to be differentiated. To simplify, this becomes 2 sine hyperbolic of x, and derivative of sine, remember, is just cosine of x. Some further identity applies here if you want to take it further, but I'm going to stop at that level. Let's go ahead and do another let's take into consideration problem 39. It says suppose h of t is equal to tangent hyperbolic of exponential of t. Question is, what's the derivative of this function? Well, let's review a couple of facts. One is that the derivative of the tangent itself, tangent hyperbolic of, say, x, we want to differentiate that, the formula is similar to the trig formula, is secant hyperbolic square of x. So another formula we need to remember is a chain rule. If I have f of g of x and I want to differentiate that, the derivative is each of these functions differentiated, multiplied, each of them applied to whatever it was being applying before. So f prime of g of x and then g prime of x. So that is the background. How do we apply here? So derivative of, first of all, this is application of chain rule. One function, and here is the interior function. Tangent hyperbolic is playing the role of f. This exponential is playing the role of g. The derivative of exterior, derivative of tangent, is secant hyperbolic square. So I write secant hyperbolic square of what? Whatever the original function was applying to, like here f was applied to g of x, f prime applies to the same g of x. Tangent was applying to exponential of t, secant hyperbolic also applies to the same thing. Second portion, the interior function exponential of t. What's the derivative of exponential? Let's remember, that's the easiest differentiation formula. Derivative of exponential is just itself. So derivative of exponential of t is just exponential of t. Now we are all done. So that was easy if we remember the basic background material. Let me do another one of these problems. Say 41, that says y is equal to exponential of cosine hyperbolic of 3x. We want to find out y prime. Need several formulas. One is that derivative of exponential itself. Just remind ourselves again that derivative of cosine hyperbolic of x is sine hyperbolic of x, and we also need chain rule. Let's see if we can do this step by step so that we don't get confused. The very last function that is applying here is exponential. So we need that differentiation formula. Now this isn't just exponential of x, it's exponential of a lot more than that. So we need to apply the chain rule. What do? We say derivative of exponential itself, so I write exponential of cosine hyperbolic of 3x. Now the chain rule kicks in. The interior function for me is this cosine hyperbolic of 3x. I have to differentiate that also. Let me just write down what I want to do and then postpone the actual activity to the next round, so too many things wouldn't be in the queue all at the same time. Let me explain what I did a second round. Perhaps using a different formula might be easier for you. The general format of this formula, when you mix it with the chain rule, is typically written like this: exponential of u. If you want to differentiate that, is exponential of u times u prime. What's the meaning of this? U is some function, some complicated function of, say, x. If you want to differentiate that, you have to remember derivative of exponential itself, and this u is playing the role of the interior function. You have to multiply by the derivative of it. That's what the chain rule is telling us here. So that's what we did here. Exponential, all of this thing is u. Derivative of that is a copy of itself times the derivative of u. Now I have to go ahead and differentiate this one. Now I rewrite again cosine hyperbolic of 3x. Now what's the derivative of cosine hyperbolic of 3x? That's really again application of this with the chain rule. It might be easier for you if you make a formula like this, cosine hyperbolic of u. If you want to differentiate that, is derivative of cosine is sine hyperbolic of u, and then by chain rule the derivative of interior function has to be multiplied with the whole thing. So derivative of cosine is sine hyperbolic. Whatever the original function was applying to, the derivative applies to the same thing. Now 3x is our interior function. This 3x is playing the role of this u here. So I need the derivative of that one also. Derivative of last 3x prime. So now I go ahead, clean everything. Derivative of 3x is just 3. I write the small things first, sine hyperbolic of 3x, and then exponential of cosine hyperbolic of 3x. Now I'm done. This is the final answer, and when the problem gets to be a bit long, we box the final answer, make sure it stands out. So these were several exercises on basic problems related to hyperbolic trig functions. You go ahead and do a few more of these problems, and hopefully you will be ready. Okay, good luck and God bless.